everyone, thanks for joining the NCL Summer Live. I'm Franz Payer with Cyber Skyline, and we run the National Cyber League. In this series, we're going to be doing a deep dive into one topic at a time to help you prepare for the National Cyber League competition. As always, these episodes are for you, and so if you have any questions at all, please ask them in the chat, and we'll get to them as soon as possible. On today's NCL Summer Live, we're going to be learning how to do file carving and basic file forensics using Binwalk. But before we get started, we need to cover the basics of files. How are files stored? How do they work? From a high level, files are just data. They're just a series of numbers. And it's the actual file type that determines how you should interpret those numbers and what do they mean. And so between like an image file, you might have a JPEG, you have a PNG. For video files, you might have MP4 files. All those different files, they all dictate a different protocol to actually read and understand the contents of a file. But other than that, the actual like what is a file, they're exactly the same no matter what file type they are. It's just a matter of like, how do I read the data? How do I read those numbers that make up that file? Computers typically store data in binary. So that's like kind of the end result of it, right? So whether you store it on a CD disk or whether you store it on your hard drive or an SSD, that data is being stored in binary. The physical way that the information is being stored is going to be different. So on a disk, it's being stored on that magnetic surface of the physical disk. On an SSD, there's another way you could do it. You can go all the way back in time to when they used when they used magnetic tape. And there's different physical ways to store that data. Fundamentally, though, every single storage medium is basically going to have a bunch of different sections within that medium. And so if you go back to the example of the magnetic tape, imagine like a film reel where every scene can store a 1 or a 0. And because a lot of these systems use magnets, you can imagine that you might have a negatively charged or a positively charged segment in that medium. And when things are positively charged, they're a 1, and when they're negatively charged, they're a 0. That's just kind of as an example. People can come up with what other mechanisms they want to represent binary, but as a simplicity, basically, there's a physical medium that can store an on or off value, which represents a 1 or a 0. And then many segments of that physical medium comprise your total data storage. And then a file is just a section of that total data storage where there's a defined start and end. And then because it's all binary, everything's ones or zeros, only numbers are actually being stored on there. And for simplicity, we typically look at files as hexadecimal values. If you're not familiar with hexadecimal, basically hexadecimal is a numbering system that has 0 to 15 possible values. It goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And the reason why we use hexadecimal rather than our normal numbering system, which is called decimal, is because hexadecimal has 16 values for every single character, and that's a power of 2, which makes things a lot easier because of math. Is a simple explanation. And decimal is a base 10, which is not a power of 2. And so if you are able to use hexadecimal, you're actually able to represent data a lot more efficiently than using binary, and that's why you typically use hexadecimal to represent the values of files. And you can use tools such as hexdump and xxd to view the values inside of a file. We're actually going to see that today. But as a summary here, you basically have the idea that there's a physical device that is storing your data. That physical device has a way somehow, whether it's through magnetism or some other mechanism, to store a 0 or 1 value, an on or off value. And then you stretch that out across many different sequences to comprise an actual data file. And you are going to have a start and stop at the beginning and end of every single file across that medium. That's how the computer is keeping track of where does one file start and where does one file end. And then within each one of those segments of the file, there are different protocols, different file types, which explain how to interpret the numbers that comprise this file. Everything's a number, and it's just a matter of, can I convert this number into text? Can I convert this number into a pixel color? The file type dictates how to convert the number into something usable. So how do you know what the file type is? You're probably very familiar with using file extensions to identify what type of file if something is. In this case here, you can see on the left side, we have this green file .jpeg. And because it says .jpeg, you might assume that this must be a JPEG file. That's not entirely true. The file extension is there for convenience. It's also a very easy way for the computer to automatically determine what file, what program should open the file. And so if the file name is .jpeg, the computer has a list of, here are all the programs that I have that can open a .jpeg. That's why when you try to open an image, you have a different program opening the image than, say, a video file. There's a mapping that your computer has of these different file extensions to the programs that should open them. That is for convenience, right? That's literally just the name of the file. It actually has nothing to do with the file itself. You can actually go and edit the name of the file and rename it to something else. So I could rename this .jpeg to a .mp3 file. And just because I changed the name of the file and the file extension from .jpeg to .mp3, it doesn't magically make the file an audio file instead of an image. And in this case here, the reason why I have a giant red X here is because someone could tamper with that and it might not actually be a JPEG. And on the right side, you can see when we use XXD, on the very right side here where you can see some of the text, you can see it says .png. And this is because there's something called a file header, sometimes also referred to as magic bytes. Typically with files, at the very beginning of the file, there is a sequence of values, binary values, which indicate what file type this file is. And it is this signature at the beginning, which is what is actually which should actually be used to determine the file type. Because you can always go and rename the file, but the actual file type is dictated by the data that is inside the file itself. And by renaming the file to .jpeg when it was originally .png, it doesn't actually affect the contents of the file, it just affects the file name. And so you can see here that the actual file itself is supposed to be a PNG, but it was renamed to .jpeg in the left example here. And you always want to rely on this right side. And when you're looking at files and you have trouble opening them and you think maybe it's been tampered with, you could try changing the file extension and seeing, does your computer now use the right program to open the file? But I just want to belabor the point here that it's not the file name and the file extension that dictates what type of file it is. It is the actual contents of the file, and the file name can always be tampered. And file names are typically, the file extension in the file name, it's typically used as a shortcut for your computer to determine what program should I open it with, because if you try to open a image file with an audio player or vice versa, you're going to have some pretty wonky results. The program's not going to know how to open that file. And so for convenience, the computer does that to figure out what program it should use to open a file. I mentioned these file signatures. You might be asking yourself, what are the different signatures for every single file type? You can actually Google this. There's a giant Wikipedia list. If you go and Google file signatures or file magic bytes, there's a giant Wikipedia list that keeps track of this. The way that it works is that every single creator of a file type, they're going to create the protocol and then they're going to publish that if they want other people to be able to use that protocol. And that's how people find out what are the different file signatures for every single file. And so what I did here is I'm highlighting the file signature for a PNG file. And you can see here that according to Wikipedia, the file signature is this 8950 4E 47 0D 0A 1A 0A. And I highlighted in the screenshot that exact same sequence when we printed out the hexadecimal value of the file using the XXD program. And so you can actually take any single file that you have, run it through hexdump, run it through XXD, and verify whether or not the actual file signature matches the file type, or the file extension in the name of the file. These file specifications, like I said, they have to be public for people to be able to use your file type. In general, you can imagine if you're the creator of the PNG file type, if you don't tell other people how it works, they're not going to be able to write their own programs to either read or create PNG files. And so it's in your best interest to make sure that this documentation is readily available and very understandable. And so even if we didn't have this Wikipedia page over here with the listing, we could go to the actual official specification, which you can see the URL here for. And it even outlines at the very top of the file here, they have the introduction and they have the PNG signature. And it says the first 8 bytes of a PNG data stream will always contain the following values. And these values are in decimal. And so to prevent confusion, I did the mapping here of what each one of these values are in hexadecimal. That's just a conversion that you can do. If you want to double check my work, you can always go and put it through a decimal to hexadecimal value converter, and you can just type in these different values here, and you'll see that they'll correspond to these hexadecimal values, which will correspond to the values that we saw in the example here. So this is how you determine what type of file something is. Now, how does this become relevant for file forensics? There's something that you can do with files to kind of hide. You can hide additional files in a single file. Or you could just say, hey, for convenience purposes, I want to bundle everything together and combine it into a single file so that if I want to transfer it, I only need to send one file instead of 100 files. You can just combine them all together into one. Normally, you would use something like a zip archive or a RAR archive, a tar archive, whatever, what have you, to facilitate that, but not necessarily. A very low-tech version of this is just combining all the files together. Combining all the files together is not very great because it is much more difficult to understand if I just combine these two files together, where does one end and where does the next one begin, right? If these are literally just a series and sequence of numbers, and I just just say this one file 1 is 10 numbers long, 10 bytes long, and then the second one is also 10 bytes long, and we combine the two together, now we have a single file that's 20 bytes long. If you don't remember that the first file is the first 10 bytes and the second file is the second 10 bytes, then it's going to get very confusing. However, there's a tool called Binwalk, which will use the file signatures to do this determination for you. And it's primarily used for analyzing firmware. Firmware will often have all of the files for running a device packed into a single file, and then it will have some sort of way for extracting all of that. If we don't have that tool available for us, then something like Binwalk will help us automatically determine how do I actually get the substantive files from here. So as an example, we're going to dive into a challenge that we have in NCL. And in this challenge, we have a image that we actually have multiple images that have been combined to form a single image. And what will happen with a lot of different file readers is that once they read a valid file, they will often ignore any extras. And so in this image here, I'm going to give you the heads up that this is actually not just one image, it's like 5 images combined together. As soon as the file viewer finishes loading the first image, it just says I'm done here, and then it ignores the other 4 images. And so from just looking at it, you actually have no idea that there are additional images hidden in this file. And so what we're going to do is I've already downloaded this. It's on my desktop here. And we're going to use the command line to analyze this and see how Binwalk is going to help us extract all these additional files. And so the very first thing that I'm going to do is I'm going to run the file command. And this is going to tell me, all right, this is a PNG file, and it's going to give me the dimensions and some additional metadata. And so you can see here that this file does not have a file name, a file extension. It's just the name, right? And so I can come here and I can rename it to greenfile.jpg. Sorry, let me do that correctly. I can rename it to greenfile.jpg, and the computer kind of got confused here, right? Before it was showing a preview, now it's no longer showing a preview because when I renamed it to .jpg, it tries to open it using the JPEG protocol, but it isn't actually a JPEG. It's really a PNG file. And if I run the file command again, you can see that even though I run it on greenfile.jpg, it still says PNG image data. And so let's actually go another level deep. This use XXD on the greenfile.jpg. And we're just gonna look, we're gonna send it to head. Head is just gonna give us the first 10 lines of results. And what we can see here is that file signature, what we discussed in the slides, and you can actually see here that when it's printed out as text, it's displaying PNG. And so I'm gonna break this down a little bit here. We're looking at raw numbers. Every single byte of the file in the first 10 lines here is being represented as hexadecimal in this view. On the left side here, this is the line offset. So this is how far, these are just line numbers in the file. And we're looking right now, every single set of 2 characters is 1 byte. Each set of 2 hexadecimal values is a single byte. And a byte is 8 bits. And so every single one of these sets represents 8 single bits of data that is being stored physically on my computer's hard drive. And the data just goes, right? It's being separated out in these columns just for readability purposes. These row numbers are also artificial. This data is a single stream. There are no segments in the actual data itself. When we are printing out the contents of this file using XXD, it is the XXD program which is putting it into columns and rows so it is easier for us to read and to view. But the actual file itself is not split into columns and rows. This is just for convenience for us to read. So at the very beginning, we had this file signature. These are the raw data itself. This text is an attempt by XXD to convert each one of these bytes into a printable character using the ASCII table. And so this 89 byte value doesn't correspond to a printable character in the ASCII table, which is why we get this dot. This 50 corresponds to the P here, the uppercase P. And if we actually want to see that, I can go and I can type in, I can actually go and type in ASCII table into Google, and I can pull that up here. And let's go and verify that. Let's look for the hexadecimal value 89. So we're going to go to the hexadecimal column, and we're going to go all the way to 89. And you can see here that the ASCII table doesn't go past 7F. 8 comes after 7, right? So it's not even on the table, which is why it gets this dot. The next character is the 50. And if we go to 50 in the hexadecimal column, we go all the way down here, 50, right? 50, second column is hexadecimal. And it corresponds to uppercase P, which is where we get this uppercase P. And then we have the 4E that follows. And so let's go here to 4E. 4E is uppercase N, and so forth, right? Image files are not, their primary purpose is to not store text, it's to store colors, and the colors are being represented as numbers. If you've ever done like a color picker, you might have noticed that they typically give you the option to specify a hexadecimal value for the color code. That is actually primarily what comprises a lot of these image files, is just numbers that represent those different colors. And the reason why we can actually see these PNGs printed out like this ASCII here, is because for convenience, the people who made the PNG file specification thought maybe it would be nice if what we did when with these magic bytes, the magic numbers here, if they correspond to the ASCII table, so it would print out PNG, so it would be more easily recognizable. They didn't have to make these number sequences here at the beginning correspond to PNG. That is just something that they chose to do, and a lot of different file specifications tend to do that just so it's more easy to recognize. But there is no requirement that they do that. If we go back to the Wikipedia magic bytes, these file signatures here, you can actually see that they're all different lengths. They don't have to be the same length. You can see here with JPEG, this is their sequence here, and you can see what it prints to, and most of it doesn't print anything readable. And the part that does, this JFIF and EXIF, they don't even correspond to JPEG. It actually, this corresponds to kind of the version of the JPEG itself and whether or not it contains metadata. They chose to make it this way. So they could have chosen to make these characters correspond to the ASCII table in this way, so that if you were to try to print them out, it would spell out JPEG, but they didn't choose to do that. And that's kind of their decision when they built it out. A lot of these additional values that print out to human readable characters, a lot of times it's coincidental. Most of this is probably meant to be an actual number, but coincidentally, if you convert that number to ASCII, it prints out something. So that's purely coincidental for the most part. This PNG at the top was definitely intentional, but again, it's up to the people who write these specifications how they want the numbers here to be interpreted, and whether or not they want them to actually print into something that's human readable. So hopefully that makes a lot more sense. If you have any questions about how that works, please ask them in the chat. I just want to reiterate that this column over here with these human readable characters, this is just a interpretation of the data in the file. It is not how the file should be read per se, unless it's intentional. And this is XXD, in this case, attempting to convert these values in the files into the ASCII table. The actual contents of the file is this, it's this row and everything below it. On the left side here, these are just line numbers, which are artificially generated by the XXD program so we can read it more easily. These actual rows and columns are not designated in the file itself. It's arbitrarily being done so, well, not arbitrarily, but XXD is choosing to display it in this fashion just so that we're not looking at a single line with all of these numbers with no breaks in it. That'd be very hard to understand. So please let me know in the chat if that makes sense, if you need any additional clarification. And we'll move on, and I'll circle back to answer any questions. But our goal here is to specifically figure out what files are hidden in this one file. And so this is where Binwalk comes into play. And so what we're going to do is we're going to use the Binwalk program to go and do an initial first pass to see if Binwalk can see any of these additional file signatures. And so I'm going to type in Binwalk, and I'm going to type in the name of the file, which in this case is greenfile.jpg. And I'm going to make this a little bit bigger. Oops, I did the exact opposite. I'm going to shrink my text so you can see this better. All right. So we ran Binwalk, and what we can see is that Binwalk is coming back with these results. There's a PNG image here, a gzip, PNG, 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 PNG. What I found a lot of the times with Binwalk is that a lot of times compressed archives like gzips will be false positives because their file signature is rather short. Uh, you can actually go and look this up. If I go to the magic bytes here, the list of file signatures, and I type in gzip, you can see that the file signature is only 2 bytes long. Each byte has 255 possible values. And so, just by coincidence, it's not crazy if you have literally thousands or millions of bytes in a file. By pure coincidence, these 2 bytes might occur back to back with each other. So you get a lot of false positives with these gzips showing up in Binwalk. Another thing that's possible is that some files actually contain segments of their file that are compressed data. And so if you open any Office document like a docx or a XLX, any of the PPTX, any of those like Microsoft Office files with the X at the end, you will find these gzip compressed datas in there because they take their file contents and then gzip them. And so you'll actually see those gzip archives inside the actual document, the actual docx. So now that we've been able to see, okay, there are other files here, we're going to try to extract them. And so I'm going to go and just search up git binwalk, and I'll pull up the documentation on how to do this. Actually, I'm going to take a shortcut. I'm just going to say extract files binwalk. This is another important skill to develop as a security practitioner, how to use Google and how to use Stack Overflow to quickly find out what you need to do. So it looks like what we're going to want to do is use the --dd command, and that will automatically extract the files for us. So I'm going to do binwalk -dd equals, and then I'm going to type in the name of the file, greenfile.jpg. All right. So what did we get? Nothing. So it didn't work. All right. Internet lied to me. I think I've run into this issue before. Typically what you need to do is you actually need to specify what type of file you're trying to extract. So let's go in here, and specifically we're looking for PNG. Let's see. Extract. Let's just see if we want to extract some images. This is like a known issue that I've always encountered this because it's finicky sometimes when when you try to look it up, when you try to auto extract it, it gets angry. So let me actually look at the GitHub binwalk. Let me look at the actual specification. How do I use your command line? Oh, here, there's a perfect example right here that I can use. So I will use binwalk -d here. I also might have made a mistake doing only one dash. It might need to be 2 dashes. And then PNG image PNG. There we go. So you can see that after we ran that, we get this new folder with all of the files that extracted. There's 5 files that actually end up being extracted here. And you can see the original here. If I open it up, that's the original file, this green square. And in addition to that, we have these like 4 additional little icons for like Wi-Fi signals. And they're named based on the file offset, the byte offset that they are inside the file. So that you can imagine that there's no rows in it, right? So this is literally like how many bytes into the file does this new image start. And you can see here that these file names correspond to these hexadecimal offsets that Binwalk told us about. What you could also do, if you don't, just to show you that you don't have to rely on the Binwalk auto extract, you can specifically identify the start and end within this file that you want to extract. And you can use the dd command to actually go and get that data and slurp it up, save it into a separate file, and then you can go and access that file. So as an example, what I'm going to do is I'm going to run through dd. And the way that this works is I specify an input file, if, and I'm going to say greenfile.jpg. And then I'm going to specify an output file. Let's just say test.png or p1. Let's do part1.png. And then we're going to do block size bs equals 1. So with dd, what you get to specify is how big of a chunk do you want to copy at a time, and then how many chunks you want to copy, and how many chunks from the beginning of the file do you want to skip. And so what we're going to do is we're going to do some math. We can see here that the next image starts at 3605. And so the first one's going to be very easy. We're going to say that the block size is 1, and then we're going to take 3605 of those blocks, and then we're going to skip 0. So to recap here, we're going to pass in greenfile.jpg, and we're going to get an output of p1.png, and we're specifically trying to get 3605 blocks of size 1 byte, and we're going to skip 0 of them. That should get us all of the data from the beginning of this first PNG to the beginning of the second PNG. And if I hit enter, we can see on my desktop that I have this new p1.png. I can open it up. I can verify that is the same file that we extracted using Binwalk. And then we can go on to the next file. And so the next file is going to be p2.png. But we might need to do a little bit more math now. So we have to skip. We're going to want to skip all the way to the beginning of the second file. So that's 3605. And we're going to have to do some basic math here. So we have 3818 is the start of the third file. And we're going to have to subtract that from the start of the second file. And so 3818 minus 3605, that is 213. And recapping here, so we are taking the input of the greenfile.jpg, the output is p2.png. We are skipping the first 3605 bytes, and we are going to be taking the next 213 bytes, which will be the entirety of the second file. If I run that here, we have the new image here on my desktop. We can open it up. It's a very, very small image. It's only 213 bytes, so it's very, very low resolution. But you can see that here, that is the second file that we extracted, and that corresponds to this one here in the Binwalk auto extract. And as a final one here, we'll do a P3, extract the third file, and let's do the additional math again. So to get the third file here, we need to subtract the start of the fourth file from the start of the third file. So 4040 minus 3818, That is 222. And we are skipping to the beginning of the third file, which is 3818. We run that again, and you can see p3.png. There it is. That's our third file here. The process is the same for the other two remaining files, right? So hopefully you don't need to see that. This is a good enough example. But what we're doing with DD here is we're specifically figuring out where is the beginning of the file that we want to extract, where is the end of the file that we want to extract, and then we're doing the math, right? We're doing the math to figure out how far into the file do we need to skip before we start extracting, and how big of a segment are we extracting into the new file. And so you could keep doing this with the other two files. And this is a practice in the NCL gym. And so you'll be able to go through and practice this yourself. Hopefully, this is a helpful explanation on how to go through and do some basic file carving with Binwalk. As a fun fact, the guy who made Binwalk was actually my boss back in high school. So this is a fun one to review because I got to see him making this originally before he open sourced it. And now it's built into Kali, which is really cool. But yeah, that's Binwalk for you. I'll open it up now. I know that there were a couple questions as we were going through. Some people asking, can you see these videos again after the fact? Yes, this exact same link that you're using to watch the video will be the same link that you'll use to watch it after we're no longer live. But you know, feel free to ask any additional questions. I think that's kind of the gist for these basics. If you have any questions about how do I extract files, how do file signatures work, how do files get stored, I'm happy to answer those questions. I'm also going to open a poll here for what topic we want to cover in the next episode. For next week, we're going to skip that episode. We're actually going to be out in DEF CON. If any of you want to see us at DEF CON, let us know. We'll try to meet up in a socially distanced way while we're there. But we're skipping next week. We'll be back the week after. It's going to be the Tuesday after next week. So let me get you the actual date for that. That is going to be, it's going to be August 10th is when we're coming back with the next episode. So I'm putting up the poll now. Please let us know what you're interested in hearing about. All right, we got some questions here. Someone's asking, can you tamper with the magic bytes? Yes, you can. So all of this data here they're just numbers, right? If I make a, let me do a quick Google search here. So I can do vim convert to hex. There's a specific command that you can use to take a file here. So I have this PNG file. I'm going to open it using vim. And then I can use, what is this? Percent, like that. Okay, so now we have this hex viewer. I'm going to go and tamper. Let's turn this 50 into a 51. And then I need to convert back. -R. Save it. And now, if I were to run XXD on it again, you can see that the 8950 turned into an 8951 and our PNG turned into a QNG. So you can definitely tamper with the magic bytes. If someone, you know, I could actually go in here, I can zero it out, right? I can go and make the magic bytes all zeros, or maybe not all of the magic bytes, but some of them just for demonstration purposes. Save the file here. And then if I try to print it out, it's all disappeared. So it is very much possible to tamper with it. It's that can make it harder to recover, right? I mean, there are ways that you could recover it if you can detect that the rest of the file is a PNG and you have that knowledge. Then even if all these bytes are zeroed out, you can go back and take the original file signature and put it back in, right? So let me go and try to restore myself. So the first 4 bytes should be this value. If I go back, if I try to, let me just demonstrate this. If I try to open this, you can see that what happened is the file viewer, it's interesting, it actually skipped the first file, which is the green one, and then it went to the next file that it could recognize. Or that, or it's tricking me. Oh, no, okay. It's tricking me. So I'll take that back. The file viewer decided to default to a past file that we had looked at. So I'll take that back. It doesn't know how to read it. It's just giving us an error here, right? So clearly the magic file, the magic bytes here prevented the file viewer from reading it. If I go back and I edit this file and I put back the magic bytes are 89, whoop. We have 89, 50, and then after 8950, we have 4E47. 4E47, like that, right? So let's put it back. Hit save, print out again, the PNG is back, and now if I try to open it, it's back again. So that's definitely something that you might need to consider, is that those magic bytes, the file signatures, they can be tampered with. And there's also a way to recover it. You just saw me do that. I went back and I put the magic bytes back in, and all of a sudden it works again. All right, other questions here. Someone's asking, what would be a clue that there are embedded files and how often does this occur? So with NCL, it's pretty straightforward. We're going to tell you that there's something wonky with this, and that's kind of your first tip off, especially if it's going to be in the forensics category, that there might be some hidden files in there. A second tip off might be a really, really suspicious looking file size. And so let's just say that for this PNG file, if I look at the properties, this one's only 4 kilobytes. But what if this file, instead of being 4 kilobytes, was like 100 megabytes, and the resolution wasn't even that great? Like, this resolution is 63 by 36 pixels. If the resolution is really low and it's a really big file, like, that seems a little bit suspicious. It seems like that there might be something hidden in there. You can apply the same thing to like audio files, right? If the audio file is like a very short duration, the audio quality is very low, but the file size is pretty big, that could be another tip off. Generally, like, if you want to be safe and you have any sort of forensics challenge, like, always run it through Binwalk. Always just see if there are any file signatures that it can pick up. All right. I'll ask one last call for any final questions. It looks like the poll is showing that you all are interested in cracking WPA and web passwords. So we're going to take a look into that on the next episode, which will be 2 weeks from now. I definitely appreciate all of you joining us today. Please let us know in the chat, in the poll, if you have any other topics that you want us to cover. We do these series for you. So again, remember that these files are they're just numbers, right? There's nothing complicated about it. It's just numbers. And then there are different specifications about how you read those numbers, and you just need to interpret them, read the specifications, look at the file signatures online. You have all these different ways to be able to understand and make use of that. And if you really want to be a nerd about it, you can read the specification by hand and go through every single byte in this PNG file and like reassemble it, right? Like, somewhere in this data is an indication of like the resolution for this image. What color should the first pixel be in the image? You can actually manually figure that out by reading the specification. So once again, appreciate all of you for joining us today. We will cover how to crack WEP and WPA passwords in the next episode. And remember, the National Cyber League competition registration opens August 23rd. And so please sign up for this fall season. We're going to have all new content. You'll get to practice this firsthand. You're going to get to be able to do challenges that will cover more file forensics. And with that, have a great night and enjoy the rest of your week.